purpose. We did this yesterday a little bit, but I'm going to go into a little bit more detail, and I need you to write some examples down. So, purpose, counting outcomes, sample space, and tree diagrams. Okay, the date is October 26th. Flipping a coin is one experiment. The coin will land on tails, or it will land on heads. Since there is only one experiment, this is a simple event. Okay, when you flip a coin, there are how many possible outcomes? Well, it's either going to be heads or tails, so there's two outcomes. So simple event is an experiment simple event is one experiment. For example, flipping a coin. Or another example, rolling a die, a number cube. One time. Okay, flipping a coin, one time. Rolling a number cube, one time. Okay, those are examples of simple events. Now, look at the spinner. What are the possible outcomes here? If I spin this right now, the outcomes, the results, I can get a 1, a 2, or a 3. If I roll this die, what are the possible outcomes? Well, I can get a 1, 2, 3, 4, 5, or a 6. Those are all possible outcomes. Compound events. Now, compound event is when you're doing two experiments. So look at the question. How many experiments will you have if you spin a spinner and roll a number cube? So there's two things you're doing. Spin a spinner and a number cube. Two experiments. So a compound event is an event with two or more experiments. Let's look at this one. So rolling a 6-sided number cube twice. So if I roll this cube 2 times, is that simple or compound? Well, it would be compound. There's a spinner with 8 sections. If I spin it 1 time, is that simple or compound? Flipping a coin and rolling a 12-sided cube. So a coin and then the 12-sided, I don't know how to draw a 12-sided cube, but you have a coin and a cube. So this is 2 experiments, so that would be compound. Now, sometimes with compound, you need to represent all the possible outcomes. Okay, and that's what sample spaces is. Sample spaces is a representation of all possible outcomes. So, for example, well, we can represent it in different ways. We can use braces. So, if you have a simple spinner like this, what's all the possible outcomes? W, X, Y, or Z. There's nothing more, right? That's the only thing that can happen. So there's 4 outcomes, 4 results that can happen. Now, if you have 2 spinners, and we did this in class yesterday, what are all the possible outcomes? Well, you can get an A with a 1, A with a 2, A3, A4, or I can get a B, right, with a 1, a B with a 2, B with a 3, B with a 4, or C1, C2, C3, C4, right? These are all the possible outcomes. And now I'm using, this is called a table, to represent all the outcomes. Now, there's something called the fundamental counting principle, which helps us figure out how many outcomes there are in the experiments that we're doing. So it says that basically all you have to do is multiply the events together to get the total number of outcomes. So you multiply the number of outcomes in event A times the number of outcomes in event B. I'll give you some examples. So here is a coin and an 8-sided die. How many possible outcomes here? Well, this coin has 2. Okay. And the die has 8. Yeah. So there's a total of 16 outcomes because the coin has heads and tails, right? So it could be heads and 1, heads and 2, heads and 3, heads and 4, heads and 5, heads and 6, heads and 7, heads and 8. And the tails could be tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6, tails and 7, tails and 8. So there's 16 possible. I mean, we'll do a tree diagram a little bit later on, but you get the idea. So here we have a cube that has 12 sides. We have a spinner with 4 sections. How many possible outcomes? 48. So we're not doing this because I don't want to do that particular example. Here is the definition, or not the definition, a type of showing the sample space, all the possible outcomes in an organized list. A type of it is called a tree diagram, and that's what we did yesterday. So we did this. So again, this, and I'll do it again. So a coin, if you flip it, you can get heads or you can get tails. And then you spin the spinner, you can get heads in 1, heads in 2, heads in 3, heads in 4. Tails in 1, tails in 2, tails in 3, tails in 4. Now, the sample space, right, you have to list so we can get, now abbreviate. You can do that. Heads in 1, heads in 2, heads in 3, heads in 4, tails in 1, tails in 2, tails in 3, tails in 4. So now the question is, what's the probability that your outcome has a head and an even number? So which of these have heads and even number? Well, we pick this one. Oops. And this one. So the probability of heads and even, well, there's 1, 2, 2 over 8, or 1 over 4. Okay. We did this again, and I'm quickly going to do it. So crust. So again, thick and thin, right? I'm going to write T-A-T-N. Regular cheese, extra cheese. Regular cheese, extra cheese. Pepperoni, sausage, vegetable. Pepperoni, sausage, vegetable. Pepperoni, sausage, vegetable. Pepperoni, sausage, vegetable. And then last one, pepperoni, sausage, vegetable. We have to do the sample space. So thick, regular, pepperoni, thick, regular, sausage, thick, regular, vegetables, thick, extra cheese, pepperoni, thick, extra cheese, sausage, thick, extra cheese, vegetable. The bottom, thin, regular pepperoni, sorry, TN, regular pepperoni, thin, regular sausage, thin, regular vegetable, thin, extra cheese pepperoni, thin, extra cheese sausage, thin, extra cheese vegetable. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different pizzas we can make. Now, if you use the fundamental counting principle, how many here? The crust had 2. The cheese, how many types of cheese? 2. Toppings, pepperoni, sausage, and vegetable, we have 3. So if you multiply 2 times 2 times 3, we get 12. Do we have 12 over here? Yeah, we do. So now the question is, what's the probability that a pizza has vegetables and thin crust? So vegetables and thin crust is this one. Vegetables and thin crust is this one. There's vegetable and thin crust. Is there any more vegetables and thin crust? Thin crust and vegetable? No. So the probability is 2 out of 12 or 1 out of 6. Okay. We did this yesterday, so I'm going to skip. Now, I want you to copy these questions, right? Because see, here is the question says, you take a survey with 5 yes or no answers. How many different ways can you complete the survey? So there's 5 questions in the survey. Question 1, question 2, question 3, question 4, question 5, right? So in question 1, how many choices do you have? You have 2 choices, yes or no. So there's 2 choices. Question 2, how many choices do you have? Yes or no. So there's 2. Question 3 has 2 choices. Question 4 is a yes or no, so that has 2 choices. Question 5 has 2 choices. So how many different ways can you complete the survey? 2, 4, 8, 16, 32 different ways. A company puts a code on each different product they sell. The code is made up of 3 numbers and 2 letters. How many different codes are possible? So the code is 3 numbers and 2 letters. And so the numbers, right, digits I should call, and these are the letters. Digits, if you think about it, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 choices. So here, I can put 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Here, what can I put? Same thing, 10 choices. Here, what can I put? Again, 10 choices. Now, for letters in the English alphabet, there are 26 letters. A, B, C, D, E, all the way to Z. There's 26. So if you're making a code, I can choose from 26 choices. And over here, I can choose from 26 choices. So if you take your calculator and you multiply 10 times 10 times 10 times 10 times 26 times 26, you get, well, wish I could tell you because I have a calculator, I do. So we're going to get 10 times 10 times 10 times 26 times 26. You get 676,000 codes. So remember, so here I'll give you an example of a code. It could be 523AB. That's a code. It could be 999ZZ. It could be 324BA. It could be 11179, right? These are codes, right? So how many different codes can we make? We can make 676,000. Okay. Hope you copied the question. If you didn't, copy now. I want you to copy this one. So my iPhone has 6 digits. My password 1, 2, 3, 4, 5, 6. Right? How many different possibilities are there? Well, now the difference with this question is that it says that digits cannot be repeated. Well, here are my choices: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, can I do 5, 5, 5? No, because it can't be repeated. Okay, so you can't repeat the same number again. So once you use it, you can't use it again. So let's, over here, what can I put? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. I can put any of those numbers. So let's say, I'm making up, let's say I use 3. If I use 3, right, I can't no longer use it. So when I go for the second spot here, how many choices do I have? I don't have 10 choices anymore. I have 1 less, right? So let me go back to this because what I meant to put over here, how many different numbers can I put, digits can I put in here? Well, I have 10 different digits. If I use a number 3, I can't use it anymore. So when I go to this spot, how many choices do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 choices. So let's say I use the 0. I can't use it anymore. So when you go over here, how many choices do you have? 1, 2, 3, 4, 5, 6, 7. I have 8 choices. Let's say I use the 5. When I go here, how many choices do I have? I have 1, 2, 3, 4, 5, 6, 7. Let's say I use the 7. When I go over here, how many choices do I have? I have 1, 2, 3, 4, 5, 6. and let's say I use a 9, when I go over here, how many choices do I have? I have 1, 2, 3, 4, 5, right? So there's a number of choices in one event times the number of choices in the other event. But you have to make sure that in this case you have to subtract 1 because you can't repeat. So 10 times 9 times 8 times 7 times 6 times 5, enter. The total number of different passwords that I can use for my iPhone is 151,200. All right, so hopefully that gives you a better idea. Hopefully copy the questions or go back and, go back on the video, write those as examples, and then you're going to finish the handout I'm going to give you. Okay?